So yesterday, the main focus from yesterday was to look at how to estimate the instantaneous rate of change from either data in a table or given a function. Okay, we mostly worked with tables. And the idea was there were two methods. You can find the preceding and following intervals. So take a preceding interval and a following interval that includes the endpoint of where you want to find the instantaneous rate of change, and then you take the average. It works, but it requires 3 calculations. Then we showed the centered interval strategy, where you pick the point where you want to find the instantaneous rate of change, you sandwich it in between the 2 closest values that are nearby, and you find the average rate of change of those, which will be very close to the instantaneous rate of change at that middle location. And both those are good ways to estimate, but they are not exact. So now, what happens if you're given an actual equation of a function? So if you have an equation, can we come up with a more exact way of finding the instantaneous rate of change? So it's not an estimate anymore, now it's an exact calculation. So we're going to be focusing on 3 types of functions: polynomial, square root, and rational functions. Okay? So so what we're going to do, so I'm going to show you on this diagram here. We're going to have 2 points, P and Q. So you're going to draw along with me here. So we're going to choose a point P over here, okay, on the function. That's going to be coordinates A, F and A, and that's the point P.
Christian, Thursday, attendance office, please. Christian, Thursday, the attendance office.
Okay, so point P is over there, and then point Q we're going to put somewhere over here. So point Q is over here. It has an x coordinate of B and a y coordinate of F at B. And so if I draw a tangent from P to, if I draw a secant that connects P and Q, okay, there's my secant joining P and Q, okay, and we talked about this last day, that the instantaneous rate of change at P would be the tangent at P. So remember, a tangent is a function, or is a line that models the behavior of the function right nearby the point that you're focusing on. So the tangent would be looking something like this. So it's a line that's kind of like it's indistinguishable from the curve if you zoomed in. That's kind of your indicator. So right now, do we all agree that the purple line slope and the blue line slope, they are not equal? Not even close, right? But we can calculate this slope of the line segment, or the line containing PQ. And I'm going to refresh your memory on a notation that we used back in grade 9. At slope, and then we subscript with capital P, capital Q, so saying it's like the slope of the line segment PQ, or we could say the line containing P and Q. And based on this picture and the coordinates, here's P and here's Q, what would be the formula, or the way you would calculate the slope of the purple line segment there, the slope of the purple line containing P and Q? So if I said find the slope from P to Q, do you know the coordinates of P? And what coordinates of Q? What would you do to find the slope? Yep.
QB minus P of A.
So the y coordinates, right? So the y coordinates would be F at B minus F at A all over. It's an average rate of change, right, guys? It just, again, this is x1, y1, x2, y2, right? It's 2 coordinates. And you're literally just doing y2 minus y1 over x2 minus x1. We're just using these as the values. We want to keep everything generic. We don't want to be specific. We want to come up with rules that work for 100% of the time, not just for specific examples. Okay. Now, if we picture point Q sliding closer and closer towards P, the secant lines get closer and closer to the tangent line. So what that's saying is, and I'm going to show you, I'm going to animate something in a second, but like you think of this point Q, if I slid point Q, so now that point Q is here, I'm going to call it Q sub 1. Okay, so I've just moved Q. Think of Q sliding along the function. If I now drew the secant from P to the new Q, it's still a secant, but is that secant a better estimate of the blue tangent? It's getting closer. It's getting steeper. Still not going to have the same slope as the blue, but it's a better estimate than it was when we used the original Q. And what would happen if I moved the Q to now be there? Is it even better? Is it getting better and better, our secants? So again, you don't have to draw this third one if you feel like your graph's getting crowded, but the idea here is my secant lines are getting closer and closer to the tangent line, and therefore the slope of the secant, or the average rate of change, is getting very, very close to the slope of the tangent, or the instantaneous rate of change. The values are getting closer and closer and closer to the one I want. Okay? So when we get this approaching, this behavior of approaching a value, we use this notation of a limit. So we say the slope of the tangent is the limit of the slope of the secant as Q approaches P along the curve. As Q gets closer and closer to P, the secants get closer and closer and closer to the tangent, and therefore the slope of the secant gets closer and closer and closer to the slope of the tangent. Okay. So I'm going to show a little animation here. I did this with my period ones, and everyone was very impressed. So I'm gonna pick a different function here. I'm gonna pick one of our parents. I'm gonna pick y equals 2 to the x, and we're just gonna zoom in over here. Okay. Let's pick a point. If I pick a point on this function to be our p, I'm gonna pick 1, 2. Is everyone okay? I'm gonna pick 1, 2. So I'm gonna plot 1, 2. Okay, so there's 1, 2 plotted. Now, this is going to be a little weird, but I want to come up with a general point that could be anywhere on the function. So if I say that my x coordinate is a, what would the y coordinate be if it's on the function y equals 2 to the x? If I said the x coordinate is generic value a, what would the y value at this point be? 2 to the a, right? 2 to the a. So look, so what happens is, as soon as on Desmos, so I'm using Desmos here, as soon as you use a letter to kind of talk about it, something in general, a slider shows up. So right now, it's a is 1, so does everyone see that the point is right on top of the one I want? But if I slide this along, okay, this is just like a generic point on the function y equals 2 to the x. So now my question is, what if I wanted to join those? I wanted to draw the line segment that joined those 2 points. Okay, so if I want the equation of a line, what 2 pieces of information do you need for the equation of a line? You need the slope, y-intercept, or you at least need a point on the line. Okay, so here I'm gonna write an equation of a line here. Y equals. Now, I want the slope. Do I actually have the 2 coordinates of P and Q right here? Right, P is my fixed point where I want to find the instantaneous rate of change. And then A2 at A is my flexible point that I want to be able to move. So if I wanted the slope from 1, 2 to A2 at A, could I come up with an expression for that slope? Y2 minus Y1 over X2 minus X1. What would be the Y2 minus 1? What would the numerator be? 2 to the A minus 2 over a minus 1. Okay, so I'm going to go to, so this is my slope, 2 to the a minus 2 over a minus 1. It's the reason it's a horizontal line right now, because do you guys see right now, this is just a number, right? This is just a constant, because right now a is 2.4, so it's just putting 2.4 into that and giving me a y value. But if I put that number, hi.
Technically not here because you said it only lessons.
All right. Okay. Now, what do you think happens if I put an x next to this? What would happen? Okay. So now, what have I done? It's going through the origin. So this is not it's not the secant yet. This is not going through 2, 1, but it has the slope, the correct slope. Okay, that's joining. Right now, the slope is joined. This would be the slope if you had the point 1, 2, and you had the generic point A, 2, and A. This is your slope, but the problem is the y-intercept's wrong. Okay. How do I fix that? Let's do transformations. So I'm gonna write something here. Do you get why that fixes the problem? I know we don't normally do this with linear, but do you get that I've just put in a D and a C for my transformations? Okay, so this is called point slope form, because the point 1, 2 is like you shifted your line over to 1, 2, and then you drew a line with this slope there. So now I have the correct slope at the correct point. If I start moving this point, you guys see I have all sorts of secants. This is secant, 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 secant. But as I get closer and closer to here, now it turns off right at this moment, right? Like, okay, so it's still there. If I make a, what do I want to make a? If I make A1, notice that it disappears. Think about what that means. If A is 1, what has just happened to my slope? If I have let A be 1. 2 to the 1 would be 2. 2 minus 2 is 0 over 1 minus 1 is 0. It can't handle this calculation. It's not, the slope doesn't exist, right? But if I just move it a teeny little bit over, do we agree that we're really, really close to being a tangent at this point? The points are like, literally, like, they're like 1.12 apart. That's how the x distance apart, and we're getting a line that's really, really close to being the tangent. So that's essentially what we want to do. We want to allow that distance, this number that's separating P and Q, we want that distance h, or we'll see what I mean by h, to be as close and get to be as tiny as possible, so that eventually we have a really exact way of coming up with what's happening at 1, I should say, at 1, 2. So did that visual kind of help to see what was happening? Because sometimes when you just look at like static pictures like this, it's hard to kind of see, but I want you to kind of see the purples are this continuous selection of secants. They're getting closer and closer and closer to being the slope of the blue. Okay? So how do we do this algebraically? So before we do it algebraically, we're actually going to do a numerical method of doing it. We're only going to do it this one time because eventually there will be an algebraic way of doing it. But let's take the example of y equals x squared. I want to find the slope of the tangent to this curve at the point 3, 9. So we're going to complete the following tables by calculating the slope of PQ for each pair of points. So notice point P is fixed as 3, 9. In the first table, point Q are all points that are to the left of 3, 9, but getting closer and closer to 3, 9. So it's like I'm sliding Q. I went to this side. It's like I kind of stayed on this side of in the picture. If I press play here, so you guys get Q could go to that side. There's nothing stopping Q from going to the other side of P, right? So I have secants on this side. I have secants on that side. Okay, so basically what I'm doing is the column on the right is me changing Q to get closer from this end, and then if I choose the other table, it's again picking values of Q that are getting closer and closer from the other end. Okay, so so we're going to grab our calculators, and we're going to start calculating some slopes. So this is just normal slope calculations, y2 minus y1 over x2 minus x1. Points, I saved you a little bit of time. I didn't just give you the x values, you had to find the y values too. Here, the y values provided. So if we do, let's do the first one. The first one we shouldn't even need a calculator. 4 minus 9, negative 5, 2 minus 3, negative 1, negative 5 over negative 1, 5. Okay? And then, okay? And then if I do 6.25 minus 9, and then divided by 2.5 minus 3, and again, if you want to try to do this all at once, you should be using brackets around the, like brackets numerator divided by brackets denominator. I get 5.5. You guys with me? 5.5. And then 8.41 minus 9, and then divided by 2.9 minus 3. Oops. Bracket. 2.9 minus 3. I'm getting 5.9. $8.9401 minus 9 equals, divided by bracket, 2.99 minus 3 equals, now I have 5.99. I bet you can kind of see where this is going. What do you think the answer to the last one is going to be? Yeah, 5.999. So look how close 2.999 and 3 are. They're 1/1000th apart. Are we feeling this is pretty close to what the tangent slope is going to be? You're literally picking 2 points that are 1/1000th of a unit apart. That's very, very, very close. I'm not getting exactly a number, but I'm really, really close to a number, right? What are we all thinking in our heads here? 6, right? Let's come from the other direction. So what if we're coming from the right? So we're picking numbers a little bit bigger than P, and notice that the values are getting closer and closer to 3, again, so that they're only 1/1000th apart. If we do the first one, 16 minus 9 is 7, 4 minus 3 is 1, 7 over 1, 7. I'll give you a hint, guys. You can use your calculator to check all these, but it's going to mirror image what happened over there. So what do you think happens next? You're going to get, well, it's getting closer and closer to 6. It's going to go down. So 6.5. And I'm getting really, really close to 6 from the other end. So it's going to be 6 point, and then 6 point, and then 6 point.
Oh.
That's even better, right? That's even closer. 6.001. Okay? So estimate the slope of the tangent from the evidence in these charts. We're feeling that the slope is 6. And think back to yesterday. Remember, method 1 was find the rate of change from a preceding interval, rate of change from a following interval, and take the average. Well, that actually worked if we chose any row here, and we did that with the 2 slopes, we actually get 6 every single time. If we took the average of 5 and 7, 6. Average of 5.5, 6.56. The average of 5.999 and 6.0016. And the thing that's getting better though, the last row is the most accurate. Okay? So far okay? Now, that's great. Do we want to do tables all the time? No. So we're now going to look at an algebraic strategy. Okay? So the idea here is instead of having the second point Q just being this number that's far, like a little bit farther away from 3, we're going to let the second point Q, okay, look like this. Okay? So point P is still 3, 9, but now point Q isn't a set coordinate. it's a variable coordinate, kind of like what I did in the Desmos example. I made it so it's a point on the function that's some small distance away from 3. So I've decided that 3 plus h is a number that's close to 3 but a little bit bigger. Okay? So in your mind, you should be thinking like h in your mind could be 0.001, but it could also be 0.1,000,001, right? It could be, we have to think of just, h is representing a very, very, very tiny number. And if you add it to 3, it's not equal to 3, it's a number a little bit bigger than 3. Does that make sense? So, and then as q slides along the parabola towards p, h will become smaller and smaller, getting very close to 0. We say that h approaches 0, and the notation we use is h arrow 0. Have we seen that arrow before in our course so far?
Yes.
We've used it to in our representation of what property of functions?
And behavior.
The end behavior. When we want to say we get close to but never equal. Remember, we had this whole conversation. You can never equal infinity, but you can approach infinity. You can never equal the location of an asymptote, but you can approach that asymptote. We can never equal 0. Because if you guys if I decided that h equals 0, I'm basically finding the slope from 3,9 to 3,9. Right? I can't because that's what would happen if h equals 0. And then I'd have 9 minus 9 over 3 minus 3, which is 0 over 0. And we do this, and we're like, what's that? Okay? But if we let q be 3 plus h, right? Then do you guys all understand why the y value will be 3 plus h squared? Because you're just putting 3 plus h into y equals x squared. So the y coordinate will be 3, take the input and square it. That's what the output would be. There's my 2 points. Let's find the slope of these 2 points, one of which is algebraic. Okay? So slope of PQ is going to be y2 minus y1 over x2 minus x1. So I'm gonna write this. I know you probably don't need to see this anymore. This is more of a grade 9 thing when you were just learning slope. But we have y2 minus y1 over x2 minus x1. So we have 3 plus h squared minus 9 over 3 plus h minus 3. I'm turning my slope into an expression, but in the back of my mind, remember, in the back of our minds, we're always thinking that h isn't a variable really, it's representing a tiny number. Okay? But for the moment, it is a variable, so we have to treat this as a rational expression. And I think we did a whole unit on that in grade 11. Do you remember simplifying things that look like this?
Yes.
No?
Yeah.
So, look at the top, look at the numerator, guys. You have something squared minus 9. That's a difference of squares, isn't it?
Oh, yeah.
So, what would the factor form of that numerator be? The square root of 3 plus h squared would be plus h. And then I add and subtract the square root of 9, which is all over. What's 3 plus h minus 3 going to be? Just h. Make sense? Let's simplify each factor in the numerator. 3 plus h plus 3 is really?
6 plus 8.
And what's 3 plus h minus 3 really?
8.
Over.
8 plus 8.
It's factored in the numerator. I can cancel out this h because it's factored. Yep.
Why is it just over 8?
Because I just reduced this.
Oh, yeah.
So,
Oh, yeah.
okay. So I get that the slope from P to Q is 6 plus h. It makes sense that my answer has h in it because one of my points had h in it. Okay? But remember, what did we say in the back of our minds? We always have to keep this in the back of our minds. That h Really is representing what again? A
Small number.
really, really tiny, minuscule number. It's still a number, it's just super tiny. Like imagine h was 0.1,000,001. And that's like ridiculously tiny number, but just put that in your mind. Then 6 plus a ridiculously tiny number, for our purposes in life, what can we basically just say? If we're having 6 plus a ridiculously tiny number, it's just 6. Okay? So that the reason how so now what I'm about to do is how do I justify that I can just replace this expression with a 6? Okay? And so this is where something called limit notation comes in.
Oh.
And this is the calculus. Okay? So the limit notation, remember we said that we're finding the limit of all the secants becomes the slope of the slope of the tangent. So we want the limit of this expression as h goes to 0. So I'll let me read the intro here. It says we use limit notation to indicate we are looking for the slope of a tangent. If it is possible to cancel h from the denominator, do so, and it is then okay to let h approach 0. The slope of the secant, the slope of the tangent to f at x at a, f at a, can be found using this formula. And whenever we use this formula, we're going to say that we're using the difference quotient. Okay? The difference quotient because it's really a quotient of differences. Okay? Because I want you to see it. Really, it's this. Remember, here's coordinate 1, a, f at a, the fixed point. Here's coordinate a plus h comma f at a plus h. That's the movable point that's sliding. Okay? And that's what you can do is this is 100% of the time this is the difference quotient. But what can we always do with the numerator? We can always reduce it to be just an h because the a's cancel out each other. And then there's this little symbol. So the short form for limit is lim. Okay? And underneath, directly underneath lim, you do an h and an arrow and a 0. So this symbol is basically saying, see this thing that's next to this? I want to simplify this as much as I can. And then once it's safe, I'll be allowed to let h go to 0. But until it's safe, I have to keep writing this symbol all the time. Because I'm not allowed to let h be 0 until it's safe to actually put 0 in. Think about restrictions. So I'm going to go back to here. We cancel this out. If this was in grade 11 and I said you just simplified this rational expression, you got 6 plus h. But then you would say where h can't be 0, right? Because if h equals 0, would this be illegal? Like at any point here, you would have gotten 0 in the denominator. Is this making sense? Okay? So here, I'll show you what I mean. I'm going to take the exact same question we've been working with. Slope of tangent equals the limit as h goes to 0 of 3 plus h squared minus 9 over h. So that was our expression that we were working with. I'm going to, just to save us some space, you're going to go see previous page. We got to the point where we have limit as h goes to 0 of 6 plus h. Right? You did all sorts of work here. You can almost think like ... There's the work you did. You would have, every step that we did on this page here would have been a separate step with limit as h goes to 0 in front. You would get limit as h goes to 0 of 6 plus h. And then this is the power of the limit notation. As soon as the h is no longer in the denominator, it's now safe to let h approach 0 because I'm not going to cause an impossible value or 0 in the denominator. Remember, this is a super tiny number that's not equal to 0, but it's so tiny it's negligible. Have you ever heard that word before? Negligible means it's so tiny it doesn't even matter. You ignore it. Okay? So 6 plus a number that's so tiny, ignore it. So what would the result for that be? Done. This is not an approximation, this is an equal. There's no dots, there's no approximation dots happening here. This is exact. Those dots are indicating that you would have had more steps.
Oh, okay.
Okay, that's not an approximation though. I don't want to confuse you. You guys get, I was trying to just do like an ellipsis, like there are steps there. Okay, but this equals all those algebraic steps with limit in front, which would end up being this, which would end up being 6. You just found the exact slope of the tangent. This is no longer an estimate, this is an exact value. So there's no, I hope I'm right, it's close. There's no like, I have to draw this and then like draw, I hope, hopefully a good tangent and hopefully pick a point on it and hopefully find a slope. Or, you know, just guess around with you picking points. You'll get an approximation. This is the foolproof way of getting an exact answer that you're not estimating with. Okay? So what we're about to do for the remainder of the period is I'm about to show you 3 more examples. We're going to go through the entire process 3 times, okay, to fully understand how this works. And then I'll let you know, I'm going to cut the homework down to just being a few questions, just so I want you to focus on this today. And then we'll worry about we'll worry about putting it all together tomorrow. But for the moment, okay, let's read each of these questions and we'll see if we can figure this out. And I'll be honest with you, every question we're about to do would be questions we would do in the first unit of the calculus unit. Okay? Because you're finding exact instantaneous rate of change. That's a calculus concept. Okay? Grade 12 advanced functions, all you need to do for grade 12 advanced functions is find estimates of instantaneous rate of change. So this is the extra topic that we're doing. So here it is. Determine the slope of the tangent to the curve y equals negative x squared plus 4x plus 1 at the point x equals 3. Then determine the equation of the tangent. Okay. So find the slope of the tangent. So slope of tangent equals, see this lovely thing in the box? The lovely thing in the box is your starting point. The A's is the point where you want to find the tangent. In this case, we want to find the tangent at 3. So everywhere there's an A, you're going to put a 3. Limit as h goes to 0 of f at 3 plus h minus f at 3 all over h. Okay, this is going to be on, first of all, this is going to be on the bonus part of the unit. This would be on the bonus part of the unit. And secondly, if I don't know what my second one is going to be. But, okay, forget it. There's no second. Okay, so there's my expression. Oh, this is what I want to say. You write that down. I'm giving you like 1 out of 5 here. Because you remember the formula correctly. Okay, and you put the right number in. So I'm giving you 1 out of 5 just for remembering this formula. Okay? Now, the rest of the process is just work with, like the f at 3 plus h, that's not, you can't work with it. You don't know what the function is. You don't know the behavior of this. So my suggestion, because our function is a little more complicated, right? It's not just x squared. Now there's a linear piece and a constant piece. I would like you to get in the habit of showing as an aside, at the side, and what is f at 3 plus h equivalent to, and what is f at 3 equivalent to. Find those values over here, and then just substitute your final answers here, so that you're not doing a whole bunch of like steps here that you can do kind of just side work and then just put the final answers here. Trying to make your work less cluttered and more organized. So over here, I want you to come up with an equivalent expression to f at 3 plus h. Now you might be saying, wait a second, there's no f at x here, but anytime you have y equals an expression, isn't that the same thing as f at x equals an expression? So even if you just quickly write like an f at x there, then I know you know what we're talking about f at x. So that expression is the expression we need to substitute 3 plus h in. So remember last year when you learned about function notation? This is what we need to put into the function. So everywhere there's an x, x gets removed, and what goes in its place? 3 plus h. So negative bracket 3 plus h all squared plus 4 bracket 3 plus h plus 1. You've been training for this since grade 10, guys. Expanding quadratics. I have faith in you. Okay? So, order of operations says binomial squared or multiplied by -1. What should I do first?
Binomial
I square first, right? Bed, e, and then mass. So the e exponent comes before multiplying. Okay. Now, I'm going to pray that you guys do not think this is good. You guys get that this is completely wrong.
Yeah.
Okay? This is not how you expand a binomial. Remember, when you expand a binomial, there's a middle term. Right? So this is, don't do that. Okay? Okay? I'm going to copy the negative. If you have binomial squared, and it's like a linear, like letter plus number, number plus letter, doesn't really matter. If you have binomial squared, the result's going to be 3-part quadratic. Okay? Now you might be saying, oh my gosh, I've been so trained that the variable comes first. I know, right? But for these ones, it's typically the other way around. Remember, 3 is your fix, and h is that tiny number you're adding. So typically for this type of problem, we put the variable second. Okay? If you put it first, it's not the end of the world, but it's just easier to see, like, here's my fixed number, and I'm adding the tiny number to it, the tiny number h. So if I do this just in the order it is, 3 squared would be 9. Now for my middle term, remember the middle term becomes first times last times 2, so plus 6h, and then square the h squared. If you just square the two pieces, you're always going to forget the middle term. Oh yeah. I shouldn't have squared the outside. I've already dealt with the squared. Thank you. Okay. And then I'm just gonna copy this because I usually this is my order of operations in my head. I go, okay, if I have any binomial squared, I'm going to deal with expanding those first. Then I'm going to deal with any distributive property, and then I'm going to collect. So 3 steps. So I'm going to do any distributive property that's required. So I have to distribute this negative, so -9 minus 6h minus h squared. I also have to distribute. I can't tell you how many times when students see this question, they do everything perfect, and then they do plus 12 plus h plus 1. What just forgot? 4h, right? You distribute the 4 as well, right? So just be careful, okay? And then if I collect the like terms, at this point, if you want to put it in the correct order of degree, it's totally fine. Negative h squared, negative 6h plus 4h, negative 2h, negative 9 plus 12 is 3, 3 plus 1, 4. So we've got this lovely expression. Does everyone see that lovely expression? I can replace f at 3 plus h with it. Before I'm done with my aside, why don't I figure out what f at 3 is as well? Okay? If I put 3 in, what number do we get? So negative 3 squared would become negative 9 plus 12 plus 1. Okay. So now, the two pieces I needed, see those two pieces, those are the two pieces that I'm going to replace in my expression. So I'm done with the aside. You got to remember to keep writing until you can put 0 in your mind, and you have to keep writing limit as h goes to 0. Okay, you can't just go like ditto or anything like that. You have to write this. Okay? So I'm going to replace the numerator with negative h squared minus 2h plus 4 minus 4 all over h. Did something interesting happen? the constants are opposite, right? The constants, the 4s, they're 4 minus 4. So what would happen to those 4s? They would reduce to 0, right? What does that mean? I have limit as h goes to 0 of negative h squared minus 2h all over h. My expression is getting simpler. Now, at this point, if I said you're simplifying this rational expression, what are some strategies we've learned from the past year to simplify rational expression? Looks like this. You could factor that numerator. What you could do, factor out of negative h squared minus 2h. Negative h, open bracket, leaving you with h plus 2. And now that you have a factored numerator, you cancel out the single h. This is the whole purpose of this. If you do it correctly, you'll be able to cancel out that single h. And after you cancel out the single h, I want you to get into a habit that you're going to write limit as h goes to 0 one more time. Because I want you to write what's left over. You cancel out that h, what is the remaining piece? There's a negative, and there's a h plus 2. Okay? So again, think of it like this. I can't put 0 in here, because I can't put a 0 in there because I would have 0 in the denominator. Can't put 0 in here. Can't put 0 in here. Can't put 0 in here. Can totally put 0 in here, because now there's no more denominator. I got rid of the problem. Okay? So now, I never actually want you to put, I don't want to visually see you replace h with a 0, because again, the whole idea here, it doesn't say h equals 0. Approach, right? So restriction, 0 is really not allowed for h. But remember, h becomes that super tiny number that's negligible, so you ignore it. So I almost would rather you think of it like the h disappears than you replace h with 0. It's a little bit of a distinction there, but I want you to understand that that's really what's happening. When you replace h with a 0, it makes it look like you're saying h equals 0, and that's not really the case. Okay? So if I let h go to 0, I'm basically saying ignore h, what's left? If h is gone, you just found the exact slope of tangent. There was no approximation here. You have found that the slope of the tangent to this quadratic at x equals 3 is negative 2. Make sense? Okay. And then half of you are like, woo, done, next question. And then you would lose 2 marks. Because read the question again. Everyone gets so excited they do this part and then they forget the last part. Determine the equation of the tangent. So here's the fun part, guys. You thought you were done with equations of lines, didn't you? You were so not done with those equations of lines from grade 9. They're back. Okay. So who remembers how to find equations of line? Anyone?
Yes.
So we want to find the equation of a line that has a slope of negative 2 and passes through the point 3. At some point in this question, have we found the corresponding y value when x is 3? Right there, right? Point, slope. Grade 9.
Grade 9 is for stretches.
Yeah.
I like them. I don't like know it, but don't ever let yourself leave.
Okay. Those of you who had me, remember this?
Yes. I know exactly what
Oh, see, it's in there.
it's just weird, I never remember doing it until
I know it's been a while. So b equals 10. So y equals negative 2x plus 10. Now, that's all great, but there is a little bit faster way to find the equation of the line. No? Okay, I think I showed you. I feel like I showed you guys. My period ones didn't say it was.
What?
Have you guys ever seen that before?
No.
Oh, yes, I've seen that. I've seen that.
From me?
Yeah.
Uh-huh. Okay, so this formula shouldn't look too shocking. It's rearranged slope. Does everyone see what I mean by that? If you isolated m on the right side, if you never saw this before, don't worry. Your mind will be blown now. Instead of 4 years ago now, or 3 years ago now, the mind blowing happens, okay? So, do you guys get, this is just your slope formula. Y, the 2's are missing, but y2 minus y1, if you brought this over x2 minus x1. The reason why it's rearranged is because to use this formula, instead of me telling you 2 points, find the slope, I'm giving you the slope and a point. I'm giving you the m and an x1, y1. Find the equation. Because if the y and the x you leave alone, you put in the numbers into the other spots, the answer will be the equation of the line. I'm also I want to show you, like, do you kind of see how it's transformations? I'm going to write something here. Don't write this yet, so you don't really need to do this. But do you guys get your M is your A value, your stretch compression. X1 is your D value. Y1 is your C value. If you take your generic point y for y equals x that starts at 0, 0, if you move that to a location that you know is on your line, x1, y1, and then just draw the slope at that point, that would be the line we want. Okay? We want the line that has this slope and passes through this point. Okay? So that's what this formula will do. So if I substitute in 4 in for y1, negative 2 in for m, and 3 into x1, if I just isolate for y, I'm going to get the equation of the line. So distribute the negative 2, you get negative 2x, negative times negative plus 6, y equals negative 2x, bring negative 4 over, and you would get plus, so you get the nice thing about this form is the answer is the equation. Whereas if you use option 1, you get the y-intercept, you have to write the equation. You get the same answer. And if you are a y equals mx plus b, or you're going to be 1 till forever and ever, then fine. Okay? But this is a more elegant and cleaner way of doing it.
Why don't we learn that at grade 9?
Because remember, distributive property is a brand new thing in grade 9. And so I think we want, because this requires knowing distributive property really well. We hope that in the 2 years since grade 9, you've solidified your distributive property abilities, and that you'll be able to handle this fine. So, and remember, guys, that this was a nice slope of negative 2. Could this be? Is there lots of cases where the slope could be a fraction?
Yeah.
So you might have to distribute a fraction, then add a number, then have to add fractions. Like, it is what it is, right? The line is the line wherever it might be. But in this case, that would be the equation line. So we found the exact slope. We put the point and the slope together. We come up with the equation of the tangent. So if I drew, just to illustrate this, okay, let's go to Desmos one more time for today. So if yeah, go ahead. So we had y equals negative x squared plus 4x plus 1. Is that our function, guys? Okay. And then we had that the point of tangency was 3, 4. And then we just found y equals negative 2x plus 10. Plus 10. Does everything fit into place here? There was the function. We plotted the point 3, 4. We want to find the tangent line. the line y equals negative 2x plus 10 is the perfect tangent to that point. Okay, and I didn't have to do any estimating. If you think about it, you didn't even really need to pick up a calculator to do that. Whereas if you start having decimals, if you started going, okay, I'm going to do preceding and following, and you want to pick a close interval, you got that you could be entering into a lot of not so nice numbers, whereas this is nice and elegant and clean and not even requiring a calculator. Okay, so that was cool. Let's do a different function. So you've now seen two examples with quadratics. Okay, the two examples with quadratics. One was just a basic y equals x squared. Now you've done one where there was some other pieces, so it's still quadratic. This one's not quadratic. This is a square root function. We want to find the slope of the tangent to that function at x equals 6. Okay? So let's start again. Slope of tangent equals limit as h goes to 0 of f at blah plus h minus f at blah all over h. I'm saying the blah because you have to fill in the blah. Okay? In this case, where do we want to find the slope of the tangent? At 6. So I'm putting a 6 in there and a 6 in there. Okay? Now, I'm going to still do an aside. There's not going to be as much to do in my aside here. There will always be more to do when it's polynomial. We have to expand and collect and everything. Here, f at 6 plus h is going to be everywhere there's an x, I replace x with 6 plus h. So everything goes under the square root. 6 plus h plus 3. Can I simplify that? Square root of h plus 9, 9 plus h. I'll do h plus 9, that's fine. Okay. Okay. F at 6 is just putting the number in. The square root of 6 plus 3 is square root of
3.
Well, 9, which is 3. Okay, so this time these are the two pieces that I'm going to put in. Limit as h goes to 0 of the square root of h plus 9 minus 3 over h. How am I going to cancel out h? H is feeling kind of trapped, isn't it?
Why are they related?
It's inside the square root. You can't just be like, oh, I'll spring it out. You can't, like, it's stuck in there. So, last year, there was a little bonus topic you did.
Logarithms?
No, not the big one. That was the big bonus topic. There was a little tiny one, rationalizing. You remember rationalizing? Here, I'm gonna refresh your memories, guys.
I kind of remember. I just don't remember what it was about. It's like, oh, kind of. This is the way it works, guys. In grade 11, in the quadratics unit, one of the sections was evaluating radical expressions, or simplifying radical expressions with roots. And in the textbook, there was adding radicals, subtracting radicals, and multiplying radicals. But then, we snuck in, like, what happens if you have a division, or radicals in the denominator. And the idea here is, if you have an expression with a radical in it where you don't want a radical, we can make it be rational, i.e. have no radicals, if we rationalize. So let me explain again, just because it probably has left your mind, why we call it rationalizing. Do you guys remember the definition of a rational number? Again, a grade 9 thing, okay? Rational numbers are numbers of the form a over b, where a and b are integers, and b cannot be 0. That's the definition of any rational number. Any number that you can write as a fraction, okay, where as a fraction of integers where b can't be 0, because that's a problem, right? Those are all rational numbers. Square roots of not like, square root of 3 is irrational because I can never turn that into a fraction. Okay? Square root of 4 is fine, right? Because what's the square root of 4? It can be simplified to 2. 2 is rational. I can write it as 2 over 1. But square root of any number that's not a perfect square is irrational. So right now, this expression has an irrational denominator because it has a radical in it. I am going to rationalize it or make it rational by making a choice of multiplying this by something. Good. It looks very similar, but the one thing that changes is the sign in between. This is called the conjugate. Okay. Tran people, do you remember this?
I remember it was C.
I remember this.
Long time. Okay. Don't worry, guys. Okay, guys. It's going to be a strategy once you remember. It doesn't matter if you learned it last year or not, but this strategy, you will have to use it for this question or else you cannot answer this question. So you need to know that for this question. Okay? Okay, guys. The conjugate, I'm going to make it really easy for you. Whatever this is, you can keep the first part the same, keep the last part the same, just change the middle sign to be opposite. You basically are creating a difference of squares pattern. Difference of squares? Difference of squares? Okay. Okay? Now, I can't just go willy-nilly multiplying the denominator by this, but if I multiply the numerator by the same thing, I'm legally, what have I just multiplied this by? 1, because it's same over same. Well, it would have been really early in the course because it was in quadratics. Okay? So what would happen here, guys? Let's look at the denominator. If you multiply, it's like expanding, first out in last, right? Root 3 times root 3 would be 3, right? Minus root 3 plus root 3 would be 0. That's the whole point of this. It's you get a 0 middle. And then positive 1 times negative 1. My denominator has become rational. The root's gone. Doesn't mean I can't. I can't just get rid of the root completely. It ends up in the numerator. But 2 root 3 minus 2. Just distributing the 2. And then you would have 2 root 3 minus 2 all over 3 minus 1, which is 2. Yeah. Yeah. And then, could I reduce? If I didn't distribute, I could have left it. Like, what do you notice about the numerator and denominator? They have a common factor of 2 everywhere. So, root 3 minus 1, this would be the overall result. Because the 2's would cancel. Okay. So, that was a refresher. Would you guys like me, as a PDF, attaching the worksheet that I gave, at least I gave my class, I was just practicing with rationalizing with numbers? Would you guys like that? Okay, I'll try and remember. Okay, so how does this work when there's algebra? It works the exact same way. So the strategy is still going to be rationalizing. So this time, the part that I want the radical to disappear from, I want right now h is trapped underneath the radical. I need to free, it needs to be freed. I need to free h. So I need to multiply by an expression that's the conjugate of this.
After school. We need to friends and learn about ourselves today. That's also
Okay, so I need the conjugate of root h plus 9 minus 3. So look what happened here, guys. The first piece, you kept the same. The last piece, you kept the same. You just changed the sign between. So what do you think happens to root h plus 9? Well, okay, so the root h plus 9, it just gets copied. It does not change. The 3 does not change. But the sign in between changes, it becomes a. And again, you can't, if you're multiplying the numerator by this, you can't just ignore the denominator. You have to multiply by the same thing. So root h plus 9 plus 3. That's what you're legally allowed to multiply by, because now you're multiplying by 1. Make sense? This is legal because it's same over same. It's like 2 over 2, I multiply by 1. 9 over 9, I multiply by 1. This thing over the same thing, divided by itself, it's 1. Okay, so what happens when I multiply? Okay, this is where our algebra is beautiful here, guys. Root h plus 9 times root h plus 9. It would become root h plus 9 squared, which would just become h plus 9. H has been freed. If you distributed the root h plus 9 here and the 3 here, do you guys get those two pieces? They still have roots in them, but they cancel out to 0. It's the difference of squares pattern. You would have positive 3 root h plus 9 minus 3 root h plus 9, 0. Gone. But then we saw the last term, negative 3 times 3. That's now your numerator. Is it making you feel warm and fuzzy, your numerator? Okay. Denominator not as warm and fuzzy. You're stuck with h and then this thing. You can't just go ignore. No, you have to still keep it. Okay? But you'll see that, remember, the problem isn't this piece. Remember, the problem is that h can't be 0. That's your problem. In here, if you put a 0 in for h in here, is it totally fine in the brackets? The problem is this h here. That's your problem. And so I cannot cancel yet. Okay? And please, I want to be very clear about this. I know probably right now you see the two cancelings that are going to happen. Do you guys see the two cancelings? What would happen first? Because I want you to do it in order. What reducing can you do first here? The 9s. The 9s come first. Don't go on a canceling spree and do everything. I won't know the order, right? So limit as h goes to 0 of h over h bracket root h plus 9 plus 3. So step 1, I reduce the 9s. Separate step. Now I have this. Can I do a separate reduction using division instead? Because now I have single h and single h. All the single h's. Okay, so we're happy when the single h's are gone. Okay, remember I said I want you to write what's left one time. So limit as h goes to 0 of, now some people make a mistake here. I canceled out this h in the numerator, but is there still something in the numerator? Yeah, when you divide by something by h divided by h, it's still 1, not 0. And then I have root h plus 9 plus 3. Now there's still an h in my expression, but is it totally safe for h to become negligible, or h to approach 0? Yeah. And again, in your mind, you can just like cover up the h. Because it's not there, you really just have root 9, square root of 9 is 3, 3 plus 3 is 6, 1, 6. This question only asks for the slope, so you're done. Lose you? That lose you? You not here? Okay.
I feel I'm gonna go home and be like, wait.
So I want you to just focus on this today. So I'm gonna tell you right now, you don't have to bring your textbook home tonight.
Ooh.
Can I borrow your paper for a second?
Okay.
On the back, so look at the back of this page that we're working on. Do you see that there are some questions there. So I am going to give you 8 questions from this paper, and you're just going to work on doing this method that we've learned today for those 8 questions. And I'm only going to pick quadratics and radical roots. So you're just practicing the example 1 and example 2, doing those ones. Okay? So on the extra practice sheet, I want you to do the following 8 questions. I want you to do 8 AB. I want you to do 9 ABC. And I want you to do 11 AD. No, there's another one. ADE. Okay. Those are the same. Those are the same 8 questions that I gave period 1 to do. Okay. All of these involve either you're doing the aside and simplifying a quadratic, or you're doing the aside and you're simplifying a square root. A couple of the square root ones are a little trickier, but I want you to follow the model that we did in class as your reference. I'm here after school today. If you want to just try and do a few before you go home just to make sure, you're welcome to stay. There's 5 minutes left in class, so maybe you can try the first one, so you're not wasting class time. Tomorrow, okay guys, tomorrow we're going to finish the last example, and then I'm going to tell you, distinguish between when you use the new method and when you use estimating methods. Lastly, before I turn off the video, your test will not be this week.
What's the possibility for you?
But my game plan as of this moment is that your test is Monday. Okay? Now, so, guys, so we'll see where we're at by the end of tomorrow. Friday is a math day, so and so the classes will be shorter. So that's why definitely not Friday. But really, there's not a lot left for me to teach. The last 2 lessons are actually kind of short, and they're actually topics that I don't focus as much on the test. So I'm going to go through them quickly, but they're not going to be a major focus for the test. Your test is going to be everything that we just did from chapter 1, all the stuff that you did the quiz on, which, by the way, you'll get your quizzes back tomorrow. Okay? And basically, the average and instantaneous rate of change estimates, all of that will be on your Monday test. Tuesday, there will be a part 2 that's bonus, and it will be on this stuff. This is going to be the first little bit that goes towards your AP bonus for this course. Okay? So, that's the plan. You cannot still be in summer. No. Done. Okay? So, that's the game plan. We were going to stick with the game plan. As far as I know, we need to get through this material so that we can remember, we want to finish by Christmas. Okay? All right. Thanks for listening.
Okay.